Okay, I'm gonna pause you guys microphone for now because I want the training not to have any feedback from the back. Roberto? Okay, good, good. All right, guys, let's dive right into the training. I'm gonna share my screen. So today, our training material are going to be on. We're going to do a whole system design. We're going to design a whole system. We're going to design a system, a standalone residential system. I sent most of these training materials. I think when the prints don't have the material, but most of you guys should have copies of this material. If not, I still have to send the material again. But what we're going to do now, we're going to do a full system design so that we all can understand what it takes to build a system, a residential system. Residential systems are systems that people use at home, resident homes. It's not a commercial base, it's just a residential, and this is DC. So there's a DC system. You have AC and DC. But a lot of similarities when it comes to designing your AC and DC system, there are a lot. So very a lot. So if you understand the DC components of the design or the requirements that makes up the systems, it's easy when you have to go to the couple or add in the AC to your configuration or your systems. I'm gonna dive right in. Let me go right into the learning objectives of this training. We are going to evaluate the standalone residential system requirements. We're going to gather and analyze the site-specific data. We're going to specify system components. We're going to examine metering and monitoring options, diagrams, and we're going to compute the system. Okay, I'm going to summarize. I'm not going to read too much. This is system application function. So we design a system for this residential area. The location is a remote area, somewhere like Lofa County or Vonjima. Somewhere remote means out of the city. Somewhere you don't have access to a lot of things you have in a metropolitan or urban settings. So we have a remote area in Southwest USA. We're going to use an elevation of 1,036,340 feet. That's the elevation of the land. The occupancy, 2 people living here year round, they live here. The client's expectation, they want a standalone PV systems. The house will not be connected to any grills, which means there's not going to be any LEC current. It's going to be a system that will not have access to grill. When they say grill, that means they are not the utility. Either your LEC in Liberia, we call it LEC. PV array provide energy year round. So they're going to depend on this PV system for a year round provisions of energy. Generator available for charging battery as backup to PV. So this is going to have a backup generator in case of days of autonomy. When they say days of autonomy in PV designs, they're referring to days that the sun will not be shining and cloudy days. We have those days in Liberia that is cloudy, it's raining for 3-4 days, no sun. There's a reason why you include a generator as a backup to run and charge your inverter as well. Now, one reason why I want to train you guys, because most of the people in Liberia who already consider themselves to know all, they had to understand that the easier way to do it is to follow the right way. When you learn something the right way and you follow the right way, you become international standardized. That means you up to the standard internationally. You can compete with a Ghanaian or Nigerian, a South African, a Kenyan, a European. When you talk about PV design or PV building, PV installation, you understand it. So it's very important that the things I teach you, not just learning it, but practicing what I'm teaching you as well. Alberto, if you guys are hearing me, you raise your hands. Oh, good. Okay, good, good. All right, great. Now, the first step in sizing a standalone PV system is to gather the consolidated data. Much of the preliminary data can be compiled by conducting a SAT analysis to evaluate the design parameters and discussing the customer's intentions and needs. Now, in Liberia, a lot of the people will tell you, say, oh, it's just 3 bedroom, or I just get it. You want to do a site analysis. Site analysis, in the sense you want to go on the site, number one, to assess the site to see if they have the space to do your mounting. Secondly, you want to know where they're going to store the battery. If the people has a small house, they want to put a battery in the bathroom, you're not going to do that. You can't put a battery in the area that is going to be occupied by people. So that's why you go on a site analysis to see what is needed. If they don't have it, you say, oh, you have to build a small little shed, a small little annex to your house for your PV systems, because we cannot put these batteries and these accessories in your residential area or the place that is people living or spend time. We can't do that. So the location for this installation is a remote area. We talked about it already. All right. Now, the preliminary design information, you need to understand the array details. When we talk about array in PV or solar systems, the array is the amount of panels, how many solar panels you're going to combine together. That's called an array. A one panel, one PV is called a model, PV model, just a refreshment for Prince to understand. Now, roof mounting, there are different types of mounting. We have roof mounting, we have ground mounting. So at different, we have pole mounting, there are different types of mounting. But the mounting for this design is a roof mounting, which means it's going to be put over the roof. So it's a roof mounting. Roof mounting, you have to understand the array tilt. It's 40 degrees. Array tilt means you bend it when you mount your panels, it's supposed to be tilted. That is why the other house that Prince went to take the picture, the roof is sloping so much that roof is almost like standing straight like this. So you can't put a panel over there because you can't even get a 40 degree or a 30 degree or a 20 degree angle. So you have to be careful about when it comes to roof mounting, you have to be careful about the tilt of the roof. You have to be very careful because that way affects how much rate that touches the panels. You have to understand all of that. There's something called the true south. When you're installing panels or model, you have to know the true south. What part of the house that the sun shines, that you will have uninterrupted sun ray. And most of the time, it's recommended that you find the true south. There are ways you can find the true south manually, and we'll go over that. Now, I talk about climate and temperature. The temperature here is negative 21 degrees Celsius and negative 60 degrees Fahrenheit. The ASHRAE extreme annual means the minimum design dry bulb temperature. The high temperature is 34 degrees. All these jargons going to be explained in bit by bit. Don't get confused. Just relax. We're going to go over it bit by bit. The battery bank design parameters. Now they're using a lithium-ion battery. I know a lot of you have not worked with a lithium-ion battery. Lithium-ion battery is the only battery you can set the depth of discharge to even 100%. You can set the depth of discharge to even 100%. What is the depth of discharge? Battery has depth of discharge, which means when you install the battery, most lead acid battery, all lead acid battery, the depth of discharge is 50%. You can't set a lead acid battery depth of discharge to 80% or 90% or 100%. You cannot. The depth of discharge have to be 50% for lead acid battery. For lithium ion, you can set a depth of discharge to 90 and above. 90, even 95, 100, yes, you can. The nominal system voltage, the battery volt equals 48 volt. This is very important. The system voltage, when we went to design the system at Bobby's house, Mrs. Whitehouse, shop, you have problem with using a 12 volt inverter on the system. Did you guys remember that the inverter would not even light on? Because the system was a 24 volt system. So you have to know the nominal voltage of your system, how many volt system you are actually designing. You have to know that the nominal voltage of your system, you have to know. For example, if your PV array, which is your solar panel, if the voltage is 24 volt, then you got to consider that when it comes to your inverter and other stuff, the battery, it comes to that, you have to understand that. The battery temperature multiplier is 1.0. We will use this when we continue. The condition battery room, the shading varies by month, 10%. You have to always allocate the shading. Shading means either dust blow on the panels or there's trees somewhere that is making the blackens, putting shadow on the panels, or you have to leave allocation for shear losses. So we use 10% shear losses. Then how we have to be allocation for your shear losses when you're doing your PV system design. In conducting the site analysis, it was determined that an array could be mounted to the roof with a standalone racking system 3 to 4 inches, 7 to 10 centimeters above the roof plane. The roof slopes and corresponding tail angle of the array is 40 degrees, with an orientation of 180 true south. The following climate data will be used for designing calculations. The action extreme annual means the minimum design drawback temperature. The annual design drawback temperature. I will show you how to get this information even for Liberia. I will show you how to get them. The temperature data above was formed from the solar ABC solar temperature reference map available online. So there is you can go to this area here. This called the www.solarabc.org and will tell you the temperature of the area you are. So I'm going to go to it right now. I'm going to take this here, solarabcs.org. Let's do a little practice here. These resources are available. You see it right here? I think it will be small for you guys, but this is the Solar ABCCS, Solar American Board for Code and Standard. So on this place, you can find the temperature of your area. There are other resources you can use also. Public news, blah, blah, blah. Let me see. Current issue, code. Okay, we'll get back to this, but they have the information you need. You can find it here, but I like to use something called the PV wax. Roberto, you used PV wax before, didn't you? All right, so you're familiar with PV wax. Now, let me say something to you guys. This is what I want you to do. Every individual in our team must take one aspect of this whole thing to be the area of specialties. If you're somebody, you can say, you know what, I would like to understand the designing part. Zach is an installer. So anything that relates to installation, he will do more reading on it, more research on it. Prince is more into marketing aspect. So he's going to do a lot of presentation. He's going to do a lot of talking to clients. So he had to understand how to present, how to talk about things that when it comes to the system and what it needs. So you have to familiarize yourself with an area of specialties. Do you understand? It makes it easy when we have people in the team that everybody has an area they are good at. Okay? All right. I'm going to leave this right here and go back to my material. We'll use the PV wax. The solar reference map. I don't know if you guys can see this here. All right, I don't want to take more time on this, but there are other resources that you can use. So let me go back to my training material. Where is it? Oh, come on. Where is it, man? I didn't close it, did I? No. Good. All right. Let's move forward. Right here, the basic system design. You see that? Can you see the graph? All right. You have your, I'm going to unmute your microphone.
Yeah.
All right. All right. I need you guys to be interactive. So can you see the screen?
Yeah.
All right. So we have the PV array, we have the charge controller, you have the battery, you have the battery-based inverter, you have the generator, and you have your AC load. So this graph is showing how the system is going to be configured. You have your PV array, your charge controller, your batteries, your battery-based inverter, you have the generator, and you have the AC components. Zach, are you asking me to either let you in?
Yeah.
Okay. All right. All right, you're connecting now. Okay, good. Now, all right, this standalone system will be configured more or less as illustrated in this diagram. So that's what we show in the diagram, how the system is going to be configured. Let's move here. The preliminary design works, gathering. Your audio is still connecting. Zach, I get a feedback from your calls.
Recording in progress.
All right. All right, good. You go ahead now. Now, so we have here, this is about the loads. This is about the load. I'm going to mute your microphone now because I'm getting feedback. All right, good. All right, let's proceed. The load analysis, average daily energy watts hour, the annually and seasonally, the total operating watts. You gotta mute that because I don't want it interfering. Okay. Okay, good. So the total, these are the loads. You know about the loads analysis, Alberto, you know that, not so? And you know we have surge load, we had the total surge load VA, and we identify the load with low power factors, the typical current load. So these are just information you get from your customer. So Prince, I'm gonna go over this for you, okay? All right, Prince. Okay, put your hand over here, me. I'm good. All right. So let me just show you a load analysis. So this is what a load analysis form look like. All right, hold on, Prince. Unmute your microphone. You want to ask question? All right, go ahead.
Go ahead. No, go ahead. I was just putting my hand up. You were asking. So
Okay,
go ahead.
all right. So I got this form right here. I'm going to show you what a load analysis form look like for those of you who have not done load analysis. Roberto is very familiar with this. I'm sure he will be able to be familiarize you guys with how the load analysis form goes. When you go to someone's house, you carry this form with you. The person have a cell phone. The load for the self, the load wax. How many wax on that cell phone, on the cell phone charger? It tell you how many wax on the cell phone charger. You check it out, they say, oh, the cell phone wax is 15 wax. You write that down on your wax load. The person have a radio, you look in the back of the radio tell you how many wax. You write that down. The pressure cooker, if they have a cooker or whatever, that's an American thing. If the person have a refrigerator, you have to check the refrigerator as well. You want to write down the load. You want to write how many watts. The person have a battery charger, fan. You want to write all those loads down. You want to write the watts. How many watts? The operation, you call the operating watts. You want to write that down. That is a very important part of your whole analysis of what it takes to build your system. You don't guess a system. It's very important. Because if you don't do this here, that's why you see people building systems in Liberia. The technician do the farm building, but at the end of the day, it doesn't last long. The battery die. This happened because why? The system was not designed properly. Then you have the quantity. How much of these appliances the person has. We see here for light bulbs, CFL light bulbs, the person has, the load is, the wax is 11, they have 4 of those light bulbs. So when you calculate the wax times the quantity, it will give you operating wax. So this CSL light bulb 11 times 4 quantity equals 44 wax. You times that 44 wax by how many hours a day they're going to use that light. Maybe you only use it at night, so they use it for 7 hours. Now you're going to take that 7 hours and then you're going to multiply it by the days per week. How many days in the week? We got 7 days in the week. You multiply it by the days in the week and divide it by the days in the week. So we say 7 days in the week times 7 days divided by 7 days equals 308. This is the average daily energy wax hour that 11 light bulb uses. So in 7 hours a week, on the average every day, these 11 light bulbs will use 308 watts hour a day. That's a very important thing you need. Then we move down to the cell phone. The person has a cell phone. The cell phone is 15 watts. They got 2 of it. You have your operating watts right here. You multiply that by how many hours to do to charge your phone. They say we do 3 hours a day we take to charge our phone. Okay, 3 hours a day. That means the person really use the phone. Like people use phone a lot. So you have 3 hours a day. You multiply it by the days per week, which is 7 days. You divide it by the days a week, which is 7 days. You get 90 watts. So you go on and on. That is how you do your load analysis. If the person have anything, any appliances, you got to ask the person how long, how many hours in the week you're going to use it. For example, let's say somebody has a TV, but they work very hard. They work a lot, so they don't really spend much time home. They're only home in the weekend, or on the weekend, I mean. Or they have a entertainment system, maybe a entertainment system like a big radio, big system with a big speaker and whatever. But the only party had a little party in the area on the weekend. So you have to know the wax out, the operating wax of that appliances, and you have to find the daily average depending on how many days they use the appliances. That is how we design systems. When you have the total daily average daily energy wax per day, the daily average is 1,314. That is it. This is a crucial information you need. That information is used to what? To size the battery bank. To size a battery bank, you're going to need the DC average daily energy wax hour. Okay? Now I'm going to give you a quick, right here, I'm going to fill that up for you because we don't have the time to fill it up. If you look right here, the DC average daily energy is 1,314. Am I right? If you hear me, put your hand up. Am I right? Okay. You're going to divide that by the DC voltage. You're going to divide it by the DC voltage. The DC voltage is the volt of the system, the panel you're using. You're going to divide that by the voltage. Okay? The system volt. So this system volt is how much? It's 24 volt. So your average daily energy amps, you have to change this watts hour to amps hour because battery is not calculated. Only one battery, one type of battery is calculated in watts hour, and that's the lithium ion. But all other battery, the lead acid battery, the flooded lead acid battery, the gel battery, they are calculated in amps, not in watts. So you have to convert this watts hour to amp hour. In order to do that conversion, you're going to divide the 1,344, which is your watts hour daily, by the system volt, the nominal voltage of your system, which is 24 volt. You have an average daily energy watts, average daily energy of 55. So that's how it is. Now, I'm going to go back here. I'm going to do small reading. All right. Here we are right here. The year-round basic load. This is the whole, I'm coming to this back to our material. TV, 200 watts. One television, operating watts is 200. Hour per day, he used the TV for 2 days. And the week, 7 days, he used it every day in the week, 2 hours. Divide by 7 days, you have 400 watts hour. That's what you use, how much of a watts hour you need to run this television. Then we have the coffee maker. Coffee maker is a big deal in developed countries. People love coffee. I cannot spend a day without drinking coffee. I'm kind of yeah.
No current here. The computer can keep battery. The battery can last long.
Oh, okay. Can you guys go down on stand for push?
The push lock.
The chair will open the push from the back. And the chair in there?
Yeah.
Yeah, the chair will open it from the back. Alberto, I'm going to continue the training. I will just send you the video so you try to do that and come back on. All right. Unmute the microphone. So the AC total operating watts is 3,038. The average daily energy watts would be 2,428. You need that information. So all these appliances they're using, these two people using all these appliances, water pump, the washing machine, the stereo, the lamp, the laptop, the cell phone charger. This is the total average daily energy watts of 2,428. Now, unmute your microphone. Unmute your microphone.
Hello?
Yeah.
Rasati. Rasati.
Yeah, go ahead.
No receptacle into the push. Pass out on the push. No receptacle there.
They can't run the children don't have an extension cord?
Yeah, no receptacle for to plug the computer charger in.
How much of a time you have?
Huh?
How much of a time power you have on the laptop?
It was so good. The thing telling us that battery low, battery low. Yeah, I need
Okay,
to plug it.
okay, I'll continue the training. I'll send you the link.
All right.
All right. I noticed that Zach was accessing it on his phone. Operator, I noticed that Zach was accessing the training on his phone. Hello?
Yeah, let's go ahead.
Yeah, I said I noticed that Zach was accessing the phone on his the something on his phone.
Yeah, his battery too burn down.
Oh, okay.
Yeah. I trying to call Stanford, but you don't want to pick your call.
That room there, when you look in the back, right to that window, always open. There's a window right over there, right on the side, right to that zinc. On that side there, there's a window over there, always open.
It's close.
It's close. It's close.
Oh, okay. All right, guys, I'm gonna continue the training. I'll send you the link. Okay. All right, let's proceed. So we have the DC average daily energy watts. We have this right here, very important information. Now, additional ceasing load estimated. They have additional load. The lights, the phonics, the refrigerator. Additional load, the total average daily energy watts is 3,850. Now, the additional summer load, 2,520. These are all the loads. All right. Final load estimate. So if right here, we're telling you all the loads and the final load estimate, the additional season load, and run from January, February, March. The load are here. This is the estimate. This is the average daily energy watts hour. Average daily energy watts hour, the average daily energy equal DC average daily energy plus AC average daily energy plus season average daily energy divided by inverter efficiency. What you're gonna do is you're gonna bind all your loads, your AC load, your DC load. Now DC load, you gotta take DC load into consideration. Even your inverter has a load. So when you're doing your system, you have to know that the inverter is going to take current because that inverter is on the system all day. So the inverter is a DC load. Your charge controller is a DC load. You have to factor that in when you're doing your system. That is why look over here. So you have your seasonal load right here. We have all our seasonal load divided by the efficiency of the inverter. The efficiency of the inverter is 0.925. To size the battery bank and the PV array, we must combine the base load energy value with the seasonal load value, adjust for inverter efficiency, and add the DC load together to get the total average daily energy required. First, the AC average daily energy base load is added to the seasonal daily energy values. Next, the new AC energy value are divided by the inverter efficiency. In this case, 92.5%. To get an accurate total AC load, finally, the DC average daily energy is added to get the total average daily energy required. DC load are not powered through the inverter, so they don't need to be adjusted for inverter efficiency. The average daily energy equal the energy All right. The average daily energy equal DC average daily energy plus AC average daily energy plus seasonal average daily energy divided by inverter efficiency. As an example, the load analysis for DC is calculated as follows: 672 watts hour plus 2,428 watts hour daily plus 3,850 watt hour daily divided by the inverter efficiency of 0.925. That will give you 662 watts hour a day plus 6,500 watts hour a day divided by 0.925 equals 7,457.59 watts hour daily. After combining all, dividing them by the efficiency of your inverter. So now we have our total watts hour daily. Since load can be varied, it is most accurate to run the load analysis on a monthly basis. By running the calculation for each month, it is easy to see any seasonal variations in the total energy use, which will ensure that the battery bank and the PV array are sized appropriately. Battery specification. We are using a lithium ion phosphor battery. The battery management system BMS monitors cells charge and discharge, communicates directly with the Shannon data monitoring system. So this is the lithium ion battery, not very popular in Africa or Liberia. We don't use much. We use more of a lead acid battery and flooded lead acid. The normal voltage is 51.2 volt. The charging volt is 54.4. The maximum volt is 58.4. The maximum volt is 44. The normal capacity is 130 amps. The nominal energy is 6,656 watts hour. So you see the difference between lead acid battery or flooded lead acid battery or gel battery compared to a lithium ion. Lithium ion will tell you right off the bat the normal energy watts hour in this battery. For lead acid and flooded battery, you have to do the calculation to get that. You have to do it. Have to do a calculation to get that. This customer has decided to use a lithium ion battery bank. Lithium ion has several advantages over other battery chemistry, like no or very little impact on cycle life from a deep depth of discharge, and the ability to operate regularly at the partial state of charge. The two don't typically require three-stage charging, so they may be able to recharge faster in some situations. One of the major downsides currently is a high upfront cost. The battery is very expensive. Very expensive. They also may have a limited operating temperature range, which may be limiting factor in some application. So limited temperature range. Some batteries don't work properly in high temperature. So if you in Africa or Liberia, I would say, and you got expecting the temperature to exceed up to 90 degrees, you want to make sure your battery is put in an area that the temperature falls within the given temperature. If you look at it, say the storage temperature is below 20 degrees Celsius to 45 degrees. That is the temperature storage. So you got to make sure that battery is stored in an environment based on the temperature storage. It's very important when it comes to battery. Now, this is a lithium ion phosphate battery. It is the best battery when it comes to designing PV system. The only back hit on this battery is that it's a very expensive battery. The reason why it's expensive because you're going to get a worth of your money or the customer will get a worth of the money. Lead acid and flooded lead acid battery, the maximum depth of discharge is 50%. For lithium ions, you can have your battery set to up to 90% depth of discharge. We will give you more current. So I just thought more about battery. I'm not going to read all day on it. Battery sizing. Now the average daily energy wax hour, which we have now, how did we got that? We got that from here, from adding all of the load. We added the seasonal load right here, the DC average daily load, 672. The AC average load, 2,428. Then the additional season load, we added them, and we divide it by the inverter efficiency. The inverter efficiency is, we convert the 92% to 0.925, we turn it to decimal. So we divide this total by the inverter efficiency to give us the total of what? 7,459. So that is how we got our 7,459. But now we explain it here better. Average daily energy, DC average energy. I want to read for you guys a little bit. Average, why you guys can't go to the carpenter guy place? He has current to his place. To the side, the guy down there, if you guys need to charge your cell phone. You know the carpenter guy down there? So the average daily energy, DC average daily, AC average daily energy, seasonal seasonal AC average daily energy. Zach, we're going to build our own mobile charging station. A small little station. We're going to need a small little a small PV array, a very like one of those 50 watts to sell. We're going to get those, and then we're going to get a little small inverter. We're going to put it in the carpenter. Going to build something, and that's going to be something we can travel with, and we're going to work on that. We're going to put a little one battery there, one 100 amp battery, and we have that charge so that anytime we have this kind of situation, you guys can have a charging station, or I can send a charging station from here. Somebody is shipping, so you can have a charging station. So in these kind of scenarios, we have a charging station. Sorry for the inconvenience at Liberia, but we have to, the ball had to keep rolling, okay? I was a little bit downsized on the whole shenanigans, but I'm good. Now let's move forward. So what it says here, the DC average daily wax hour is 672. The AC here is 2,428. The seasonal wax is 3,850. Now let me ask you a question. Unmute your microphone. So you build a system, you are designing a system for a customer. And the person tell you that I live in okay, I'm gonna ask you guys a question, okay? You are designing a system for a customer. The person tells you, I live in America, so I'm not in Africa all the time. My refrigerator, my air condition, my television, those appliances are not going to be used when I'm not in Liberia. And usually I go to Liberia for the Christmas, so I'm there in December. I'm there for a month, or I'm there for 2 months. What type of load are those loads? Are those AC load, or are they seasonal loads? You have to unmute your microphone. Okay, never mind. I think your audio bar on the phone. All right, never mind. Good. Never mind. Forget about it. You guys can hear me? Just put your hand up. You hear me clear? Are you guys hear me clear? Just put your hands up. Oh, good. All right. Don't be responsive. Let me just continue this training Okay, forget about it. Let me just continue. All right, let's move. So we have this right here. You have you have to divide all your loads by the efficiency of your inverter. So when you get an inverter, when you're going to buy an inverter, you got to check the inverter efficiency. Now we'll come to something that has to do with what kind of inverter to use based on the load or based on the system you are designing. So this says here, after all our calculation here, after adding 672 to 2,428 to 3,850 and dividing it by the divergent efficiency of 0.925, we have 6,590. Now, why is that? As for example, okay, average daily energy equals DC average daily energy plus AC average daily energy plus seasonal load divided by inverter efficiency. That's what we just did. Or I'm going to move forward. So that's how they got this total load. This is the battery. This is a lithium iron phosphorus battery. It's not very popular in Africa. It's a very good battery. Very good. It's expensive though. Very expensive. But this battery here is, oh my God, so no maintenance required. It has its own battery management system. It's a perfect battery for bigger jobs. Real nice battery. Real good battery for people who got a little bit of green hands. So in Liberia, we don't have much opportunity to use the battery for now, but we're getting there. We're recommending it now as we go forward. So let's move. Let me read a little bit. For this system, we have choosing a discovered lithium iron phosphorus battery, a chemistry commonly referred to as a LFP. This battery, like most lithium ion battery used with PV system, must be on order at the required normal system voltage. In this example, the normal system voltage is 48 volt. And so the discovered battery we are using is 48 volt. Now, why you need 48 volt? You cannot pair this battery in series. You cannot pair them in series. You can pair lithium ion battery, you can pair flooded lead acid battery to give you the required voltage you need. But for a lithium ion battery, you can't. I'm sorry. Lead acid battery can be paired in series, but this battery cannot be paired in series. You can't pair this battery. You can't pair it. So I'm running out of time. So let's move forward. The battery sizing. Now let's size this battery perfectly well. The average daily energy watts is 7,259. You get it, Zach. Are you copying? Put your hands up if you're hearing me. You copying. The average daily energy watts is 7,459. The days of autonomy. I'm going to go to my key here to show you. This is the calculation I do right here. This is the calculation. Average daily energy, this is just an example. Here is 55. The days of autonomy is 5. The depth of discharge, this is 50%. But if you look here, under this material here, average daily energy, days of autonomy, which means the days that you set your battery for how many days your system can run only on batteries. On very flooded day, cloudy days or rainy days, you're going to need to size your battery based on that. If you don't size the battery with considering the fact that there are going to be days of autonomy, then you have to tell the customer you need a backup generator. So that when it's raining, we can put a generator on so the generator can charge your battery. You have to let the customer know, because this is going to be a conflicting issue in the future if you don't let them know. The people think that they're going to have current 24/7. Now it's raining 2-3 days. You don't exhaust the battery. The battery doing ping, 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 and reading a light, letting you know that the battery is exhausted. The customer is angry because you didn't put this forward. That's why we do the thing the right way. That's why we read. I was saying to somebody in Liberia who act like they're very too smart. I say, you have to read to understand things. Whoever write things on the paper is for understanding of people who don't understand it. That's the whole purpose. Now, if you look right here, we have our depth of discharge. Because it's a lithium iron phosphorus battery, the depth of discharge is 90%. If you look at my little graph here, the depth of discharge is 50%. 0.5 is 50. So this is 50%. So for lead acid battery, your depth of discharge max should be 50%. Very important to set your depth of discharge. That's why people say, oh, the battery can last long in Liberia. The battery can last long. The battery can last long. When you do a system, you don't set the depth of discharge. The battery run out. And if the battery run out, it hits 0. That battery can never take charge again. It will not be able to take charge. So this is very important. Always read the manual. The battery come with it tell you, look at the inverter. The inverter will tell you how to set the depth of discharge of the battery when you configure or install the battery to your charge controller. Your charge controller. If you have an inverter charger, it also will tell you how to set the depth of discharge for your battery. You must learn these things. Depth of discharge is very important. If you make mistake and you don't set a depth of discharge, this person run the battery. It's not the lithium ion battery. They run it all the way down to the ground. Now the battery can never take charge again. They have spent thousands of dollars to buy a battery bank that can't take charge. And you're gonna be in a big charade. Gonna be in a big mess. Okay. Let's move back here. All right. This is sweet. Now let's move right back here. We have your depth of discharge of 90%. The battery temperature multiplier is 1.00. 1.00 is the battery temperature multiplier. The battery will tell you the multiplier of the battery is on the specs of the battery. They tell you the temperature multiplier of the battery. Most battery is lead acid battery. Some of them is 1.11. But you need to know the temperature multiplier of the battery when sizing the battery because that is included. So we have average daily energy watts times the days of autonomy divided by depth of discharge times temperature multiplier. Required battery needed, the required battery bank capacity would be 16,576. Are you seeing that? Now there's software I can use. It would take me 5 minutes to do all of this. But I'm going to teach you guys the hardware first before going to the software. You must learn the hardware first before going to the software. So if you don't have access to a computer or something, you can take a pen and paper and do the math quickly. That's just the difference. That stands you up. So right here, they just told us that this is our battery bank capacity. To run a 7,459 watts hour daily system, you're going to need 16,576 battery bank capacity. Vani, are you getting this? Zach, are you getting this? Raise your hand if you're hearing it. Are you getting it? Good. All right. I'm going to have you guys do your question and answers and you send it to me on WhatsApp or Messenger. You can tell any question answer. You can send it to me on Messenger or WhatsApp. You can text it to me because the internet's bad. Now the battery capacity watts hour divide by the battery capacity. Now this lead acid battery, this lithium ion battery, one battery, is 6,650. One. Now let's go to our small battery we're using because I don't want to confuse your mind. We have small battery we're going to use. So right here, I'm going to use the same system. Your average daily energy watts hour is 55 times the days of autonomy 5 days divided by your depth of discharge 0.5 multiplied by the battery temperature multiplier of 1.05 gave you the required battery bank capacity of 578. Now, the required battery bank capacity amps hour is 578. You're going to divide that by the battery amps. So this is a 225 amps lead acid battery. So you divide it by that. It tells you how many battery you need, battery parallel in string. 2.6. You're going to round it up to 3 battery. Do you get it? I'm going to the big board now. This is just a small board. They're going to go to the big board. Let's go over here. We come here. They said 6,655 watts hour. So let me look at the battery again. Let's go back to that battery. Here's the battery right here. There's one battery bank of a lithium iron phosphate battery. The nominal voltage is 6,556 watts hour. You seen it here? 6,656. That's the energy watts hour. So that is why over here they're using it to divide to find how many battery they need in parallel and string. Number of battery in string in parallel. 2 battery. Because it's 2, we can use half battery. We have to round it up to 3 battery. So to run 6,459 watts hour system, 7,459 watts hour. How do you divide this and change it to kilowatts? Where is Mr. Where is Alberto? Alberto. Is Alberto there? Okay, good. Can you tell the guys how to change this watts hour to kilowatts? Good. You divide the 7,459 by 1,000. So you say 7,459 divided by 1,000, 7.4. So the kilowatt system we're talking about is a 7.4 kilowatt system. That's a 7.4 kilowatt system. So when you see 7,459, if you change that watts